All right, so let's get started, guys. Triple integrals in cylindrical coordinates, or as some of my students last year like to call it, polar plus z. So let's a reminder for cylindrical coordinates. X is our cosine theta, just our conversions. Y equals r sine theta, and z equals z. Those were our important conversions. Now, when we just a few days ago, when we talked about polar coordinates, we came up with an expression for our area element in polar coordinates. So let's draw that again. Remember what that was, because we're going to be using that for cylindrical. So this is pi over 2, the pi over 2 axis. This is the theta equals 0 axis. And we drew a little area element in the polar plane. And we said our area element was, the coordinates were delta r sub I, and this was delta theta sub I between these two. Oops, not Q. And the area, we said the area was of the little element a sub I, or we'll call it delta a sub I. Delta a sub I was the average radius of that sector times delta r sub I, delta theta sub I. And that's how we developed our double integral in polar coordinates. Now we're going to use this area element to develop our volume element in cylindrical coordinates. So if we take this and we add a coordinate axis here, we add our z-axis. Let me move over just a little bit. So we're just going to add a z component to this. So this is my z-axis, and down here I'm still in this plane rather than the xy plane. I'm in the polar plane. So this is pi over 2. Sorry, this is 0. And this is theta equals pi over 2. And if we take our area element, we would be down here in the plane. Like so. And this is, on this side is delta r sub I, and this is delta theta sub I. And the arc length is the average radius times delta theta. And the area is still the average radius times delta r times delta theta. Now we're going to project this up, and we're going to make a volume element up here above the plane. So here's our little, let me make this a dotted line. We're going to make a little volume element here. Let me redraw this. I want to make this this way. And we're going to make a little kind of cylindrical, a section of a cylindrical rectangle. And rectangles in quotes here. So there's our little volume element. And this difference here is just delta z sub I. So I'm just projecting this up above the plane here. So our volume of this little element, delta V sub I, is going to be the area of the base times the height. So it's going to be our average radius, R sub I, times delta Z sub I, times delta R sub I, times delta theta sub I. So that's our little volume element using cylindrical coordinates. I'm just projecting this area up, and I'm making a little kind of rectangular shape. So the volume is going to be the area of the base times the height. And we're going to sum these volumes over our entire region. So we're using the same arguments that we have before. So we're going to sum all these blocks over the region that we're interested in. Take the limit as delta V sub I gets very small. And again, we're being a little loose with what we're actually doing, but in terms of understanding the concept, that will work. We're making delta R, delta theta, and delta Z extremely small and taking the limit. So we can define our triple integral in polar coordinates with this as our volume element. So is everybody clear on what we're doing here? All right. So our triple integral in cylindrical coordinates. The triple integral over our region of f of x, y, z dv equals the integral from theta 1 to theta 2, the integral from g1 of theta to g2 of theta, and my inner integral is going to be some function of r and theta, h1 of r and theta to h2 of r of theta, of our function expressed in terms of r and theta, f of r cosine theta, r sine theta, z, and I need a little more room here, r dz dr d theta. And this r dz dr d theta is our volume element in cylindrical coordinates. So we're just like we said at the very beginning, it's polar coordinates plus z. So we're just adding a dz to our volume element. We still have r dr d theta. And if we look at, once we do our inner integral with respect to z, our outer two integrals are just our integral in the xy plane, or in the polar plane. So this integral and this integral are double integral in polar coordinates of the region. So we integrate with respect to z, and then we get back to polar coordinates in the plane. And what we're saying here, just so we know what we're talking about, theta 1 is less than or equal to theta, less than or equal to theta 2. So theta is varying from theta 1 to theta 2. g1 of theta is less than or equal to r, and that's less than or equal to g2 of theta. So r is varying from g1 to g2. And h1 of r and theta is less than or equal to z, less than or equal to h2 of r and theta. So we're just expressing z in terms of r and theta, and that gives us our limits of integration. And the way that I've written the integral here is for a radially simple region. And just like in rectangular coordinates, we have 6 possible orders of integration. Usually we're going to express our integrals as usually we're going to use the order r dz dr d theta. And we use that for a region, if our region is easily expressed in the xy plane in terms of polar coordinates. This order makes the integral easy to do. All right, any questions on the development? Pretty straightforward in terms of what we've talked about before. We're just extending polar coordinates into the third dimension, essentially. No questions? All right, so let's do some examples. Just like with the other integrals, the difficulty in these is often in the setup. So we're going to set up a few of these integrals. So let's look at the integral from -2 to 2. The integral from negative square root of 4 minus x squared to square root of 4 minus x squared. The integral x squared plus y squared to 4 of x dz dy dx. We want to convert to cylindrical coordinates. Because just looking at this, I don't like this x squared plus y squared. I don't like these radicals. So let's see if we can convert this to polar coordinates. All right, sorry, cylindrical coordinates. So we're going to look at our limits. The inner limit tells us that x squared plus y squared is less than or equal to z, less than or equal to 4. And the second integral tells us that minus square root of 4 minus x squared is less than or equal to y, less than or equal to square root of 4 minus x squared. So we need to have an idea of what this looks like, and we also know that x, the -2, less than or equal to x, less than or equal to 2. So we need to know what this region looks like. So we'll do a quick sketch. What is the equation z equals x squared plus y squared? What's the graph of that look like? So I hear a circle, I hear a hyperboloid. Paraboloid. So if we let y equal 0, we get a parabola in the xz plane. If we let x equal 0, we get the parabola in the xz plane. So we get this paraboloid. And the upper limit on z is 4, so the paraboloid is kind of cut off up here at z equals 4. And this surface is z equals x squared plus y squared. And in the xy plane, what is this in the xy plane? A circle with radius 2. So in the xy plane, we get a circle. X squared plus y squared equals 4. All right, so we have our region. And just looking at this, I like the way this looks for polar coordinates, for cylindrical coordinates. For our surface, z equals x squared plus y squared, how would I represent that in cylindrical coordinates? Z equals r squared. And I think we're good here. So let's set up our integrals. So our integral in x in cylindrical coordinates, not the limits, but here we're integrating x. X is our integrand. So how do we represent x in cylindrical coordinates? R cosine theta. Very nice. All right, so now we can set up our integrals. We have everything we need. So our integral, I'm just going to write equals. So let's set up our limits. Z varies from, in here, it varies from what to what? I'm inside here. 0 to 4. 0 to 4? R squared to 4. I'm going from, if I set up a little rectangle, my Z is in there. So Z equals R squared to 4. The radius in the xy plane. Radius goes from 0 to 2, right? My radius is just the radius of the circle. Radius is 0 to 2, and theta equals, we could do 0 to pi halves and multiply by 4, or we can just do 0 to 2 pi. And my x is r cosine theta, and then I have dz, I'm going to write it this way, r dz dr d theta. Not a difficult integral to evaluate. Pretty easy one. But let's be smart. Let's look at our original. So we've solved the problem. We've switched to cylindrical coordinates. But let's look at our original problem. Thinking about the quiz that we just took. What is the triple integral over a region of x dv? What is that? yz, myz. So this we're doing a triple integral. It's a triple integral. So it's the moment about the yz plane. Looking at this shape, what's the moment going to be about the yz plane? It's symmetrical. 0. It's symmetrical, so the moment, if we sum the mass on one side of the yz plane and add it to the mass weighted by its distance from on the other side of the yz plane, they're going to cancel, right? Our coordinate of our center of mass is going to be on the z-axis. So this integral equals 0. So you didn't even have to evaluate it. We looked at this and we were smart, we were clever, right? We had to be clever. And we saw that our integral was 0. And we didn't have to evaluate it. Any questions on that?
Are you going to do a problem like that on test or quiz?
Well, you could. This would not be difficult to evaluate.
You could evaluate it.
You could evaluate. It's not a hard one to evaluate.
But then I'll get 0. I'll be like, shoot, I was wrong.
You think you got the answer wrong if you got 0?
Yeah.
Yeah. All right. Let's look at another example. A little more complicated, but not that hard. All right. Another nice one. Cylindrical coordinates, spherical coordinates are so nice because it's a fun way to think, I think. We want the volume of the solid inside x squared plus y squared plus z squared equals 4. And above the upper part of the cone, z squared equals x squared plus y squared. So we're looking for this volume. Cylindrical coordinates are usually going to be easy for a region that has symmetry about the z-axis. So if you have symmetry about the z-axis, that's going to suggest cylindrical coordinates. A sphere and a cone, the sphere and this cone both have symmetry about the z-axis, so that would be my first thought is cylindrical coordinates. So let's make a quick sketch of what the region is that we're looking at. X squared plus y squared plus z squared is what? What kind of shape? A sphere. So it's going to be, and its radius is 2. So I'm just going to draw it here in the first octant. So there's my sphere. And z equals x squared plus y squared, the problem tells us it's a cone. So we're going to have a cone that goes up, and we're looking at just the upper portion. So our cone is going to be here, and our intersection is going to be along here. So we're looking at the region that's inside, between the cone and the sphere in this region. So we need to do a couple of things. We need to figure out our region in the xy plane. So if we project this intersection down, our region of integration is going to be some circle in the xy plane, and I'll make that dotted.
Mr. Beamer, I'm confused about the shape that we're looking at. That dome right at the very top above the cone there?
Everywhere, so we want the volume that's between the cone and the sphere. So we're inside the cone, but below the sphere. So it's like an ice cream cone. So we're looking for the volume of the ice cream. Yes.
Okay.
So the volume of the ice cream inside this cone.
But
So
it's including that.
this is where it's sticking up above. So this is where our scoop is sticking up above the cone, and we're finding the volume of all the ice cream all the way down to the point. And it's a really nice ice cream cone because the ice cream is all the way down to the bottom. You don't have a big empty spot. All right. So what do we need to do to figure out what our region is in the xy plane? Well, we have to draw it, but we need to get an equation for it.
Yeah.
So the circle here where the cone and the sphere intersect, how can we represent that in terms of what we have here?
That's when z equals 0.
Well, z equals 0 right here. So what we need to do is on this intersection, z equals x squared plus y squared. So I can plug in z for x squared plus y squared here. Because on that intersection, z equals x squared plus y squared.
Square root of 2.
So on the intersection, we have z squared plus z squared equals 4, or 2z squared equals 4. So z squared equals 2. And z squared is x squared plus y squared. So in the xy plane, x squared plus y squared equals 2. So now we have a region in the xy plane. So we'll draw a quick sketch of that. In the xy plane, we have this circle, and this is x squared plus y squared equals 2. Now we're ready to go. We want the volume. Let me scroll up just a little bit. Volume is our triple integral. Z varies from what to what? It varies from the cone to the sphere. So on the cone, z equals x squared plus y squared in cylindrical coordinates, or z squared equals x squared plus y squared. So z squared equals r squared, so z equals r. So z varies from r to the cone, or I'm sorry, to the sphere. Z equals, on the sphere, z equals what? Square root of 4 minus r squared. R varies in our region in the xy plane. R varies from 0 to square root of 2. Theta varies from, we could do 0 to pi halves and multiply by 4, or we can say 0 to 2 pi. either way. And our volume element is r dz dr d theta. I'll just do the first integral. So we end up with the volume equals the integral from 0 to 2 pi, 0 to square root of 2, and my first integral gives me r times the square root of 4 minus r squared minus r squared dr d theta. And from here it's very easy. Very easy integral to evaluate. If you go through to the end, you would come up with 8 pi over 3 times 2 minus square root 2. So that's the volume of my ice cream inside that cone. And just imagine, look at our region, our dependencies for our functions. Imagine doing these integrals in cylindrical coordinates. This would be very painful with all these radicals and the squares and the intersection. It would be very painful to do in rectangular coordinates. This is a very easy integral. Any questions? All right. I think you guys are going to like this one. There you go.
Are your problems long? I feel like you're tricking us.
Now the nice thing about these, the nice thing now is that we have all these tools, so you have the ability to switch back and forth. You can say, oh, I need to do cylindrical coordinates here. I need to do spherical coordinates here.